Hi everyone, welcome to my YouTube channel. In this video, I'm going to talk about heap sort solution to Leetcode question 912, sort an array. Heap sort has time complexity worst equals average equals best equals O(n) log n. And the space complexity is O1. It does not require additional space, unlike the merge sort. Let's review the binary heap. Binary heap is also a complete binary tree. So in this case, we need to consider how to represent the given array to a tree. We use this representation. For parent node index I, the left child node index is 2 times I plus 1, and the right child node index is 2 times I plus 2. So given the parent node index I, we can find the left child node index and the right child node index. How about given a child node index I, find the index of its parent? There are two different scenarios. First one, if this child is a left child, in that case the parent node index equals I minus 1 and then divided by 2. Because I, the child node index I, for the left child is the 2 times parent node index plus 1. Similarly, we can use this logic to find the parent node index if this I is a right child. So in that case, combine two scenarios together, we can get the parent node index, which is I minus 1 integer divided by 2. There are two main types of heap. Mean heap, where the parent node value is less than or equal to the children node's values. So the root of the mean heap is always the smallest value in the heap. The max heap, the parent node value is greater than or equal to the children node values. So for max heap, the root of the tree is always the maximum value in the heap. Python has a built-in implementation using heapq. Let's just quickly go over and review some common functions implemented by heapq. This heapq is a mean heap. It has heap push. You can push the value item onto the heap, maintaining the heap environment, which means after you push the item onto the heap, you just sort the heap to make sure that, or reheapify, just to make sure that the heap maintain or remain as a mean heap. And then heap pop and return the smallest item from the heap. After return this item and pop this item from the heap, it reheapify to make sure the remaining items remain as a mean heap. If you do not want to pop the item from the heap, you just want to access and know what is the smallest item or smallest value, you can just call heap 0. There is also option heapq heap push pop. It means it first pushes the item onto the heap and then pop and return the smallest item from the heap. According to Python documentation, it is more efficient than you first call the heap push function and then call heap pop function. It's just one function doing two things together. Heapify x is given a list of x. You can build a heap, transform that list x into a heap in place and also in linear time. So the time complexity is O(n). So now let's talk about the heap sort algorithm. So the max heap is to sort in ascending order, to sort the array in ascending order, and the min heap is to sort the array in descending order. Why? It will become more intuitive as I walk you through the algorithm. So let's remind ourselves, if all the subtrees in a binary tree are max heaps, the entire tree is a max heap. So the key idea for the heap sort algorithm is to first build a heap. So we want to create a function called heapify. So just this heapify is building a max heap. So the first step is to build a max heap. But which node should we start to build this max heap? we start from the second to the last layer, or start from all parents in this binary tree from bottom up, which means, okay, if we look at this tree from top to the bottom, at the bottom are the leaves. We want to consider one layer up from the bottom, that is all the parents in the binary tree, to create a mass heap. Basically, we are creating this heap from bottom of the tree and moving up. Since this problem is sort the array in ascending order, so we are building a max heap. So in that case, since given that we are start from the parents nodes, from the bottom up, so that's the index is starting point is actually the length of the array is n. N minus 1 indicates the last index, or the index of the last elements. That's our leaf node, guaranteed to be, that's our leaf node. Well, that's not actually, well, if the tree has more than one node in the tree. So that's kind of the index. And then remember, we go over how to get the parent node index given the child node index I. So we start from the rightmost child node index, that is n minus 1, and then we use that to calculate its corresponding parent's index, and then that's our index starting point. And then the next parent index is just this minus 1. Okay, the first step, given a parent node index, we compare the value with the values of its child nodes. We compare with the values of left child and compare with values with right child. And then if we find the child node value is greater than the parent node value, we swap the child with the parent. And then we repeat step 1a and 1b for the swapped child node. So that means, okay, after we swap the value for this child node with this parent node, we want to call the heapify function for the tree starting or with root at this child node. What if both children is greater than the parent? In that case, we swap with the larger one. That is because we are trying to build a mass heap, so we are always trying to push the maximum value to the top of the tree. And then second step is, after we create a max heap from step 1, we just create a sorted array from our max heap. How do we create a sorted array? We first swap the heap root with the last items of the heap. So this operation is to put the maximum value of the entire heap to the end of the array. For example, for the very first iteration, when we first call it, because I'm calling it for the very first iteration because we are going to call this step 2 recursively. Not recursively, sorry. We are going to call this step 2 iteratively as well. For the first iteration, we swap the array 0 with array n minus 1. So array 0, remember now we have a max heap. So array 0 represents the root of this heap. So that's guaranteed to be the maximum value. And then the array n minus 1 is the rightmost leaf of this tree. So after swap, we put this largest value to the end of this array. So that's what we want. If we want to return this array sorted, we want the maximum value to be at the end of this array. So that's why we swap it. And then after swap, we are going to reduce the heap size by 1. and then re-heapify. Reduce the heap size by 1, it means, okay, for the first iteration, after step 2a, we only heapify the elements array 0 to array n minus 2 because we already put the maximum value onto the last position. We swap. Remember, in the 2a, we performed the swap. So that's why we already have the maximum value in its correct position, in its correct order. So after that, we only need to consider the elements from index 0 to index n minus 2. So in that case, we perform heapify in order to get the maximum value of this subarray to the top of the tree. And then we can repeat step 2a and 2c recursively. In the next iteration, we're just going to swap the elements array 0 at the index 0, which is maximum value of this current heap, with the elements at position array n minus 2. That is the swap for the second iteration. So this is our entire algorithm. So let me recap. The first step for sorting an array in ascending order using heap sort is to build a max heap. Basically, we create a function, call it heapify, and then use it to build a max heap. It's a recursive function. And then in the second step, after we already have the max heap, we are just going to create a sorted array from this max heap. So that's the key idea for the heap sort algorithm. So now let's go to the part where we calculate the time complexity. So for the step 1, we have a very important component. That's our function heapify. We need to call this function recursively to build a max heap. So first, for a heap of size n, if we are calling heapify for only one tree node, in the worst case scenario, we need to swap through all the levels until reach the leaf nodes. For other scenarios, we may stop in the middle because, okay, this is already greater than or it all is children value. And the reason why we start with the bottom up, because we want to make sure that, okay, all the children, all the child's nodes are already, all the children subtrees are already satisfy the max heap condition. Remember, if all the subtrees in binary tree are max heaps, the entire tree is a max heap. So to calculate the time complexity, calling the heapify for a tree node. And then in the worst case, we need to swap through all levels until we reach the leaf nodes that we need to swap through the levels. So OH, where H is actually the height of this tree. So that's the time complexity for calling heapify for a tree node. And then this H could be 0 if this tree node is at the bottom of the tree. We do not need to do any swap. And then it's log n if it's at the top. That is because we need to, for a heap of size n, the height of this tree is log n, the width base 2. So in that case, if we call it heapify for tree node at the top of the tree, the worst case scenario, the time complexity is log n. So that's why, now we can see, that's why in the heap queue implementation, the heap push and heap pop, they have the time complexity O log n. That is because, okay, those items, that is because kind of like what related to this part. So if it's at top, it's log n. And then for heapify time complexity, we need to call the heapify for all the tree nodes. So in our case, it's the sum of O H times the number of nodes at head H. And then for binary tree, the number of nodes at head H is actually less than or equal to n divided by 2 to the power of H plus 1. So apply this one to this equation and then calculate it using math. You can derive at the results that is On in the end. So we have covered the main idea for the heap sort algorithm. So now let's start coding. So for step 1, we need to apply heapify from bottom up. And then the step 2 is to sort after create a max heap. So in that case, it means we need to have a function, we call it heapify. And then we are going to input the numbers, this array. And then we also need something as this node index. So in that case, and then if we want to apply heapify from bottom up, we just need to loop through. Remember, the parent node index for the rightmost child is n minus 1 minus 1 and then divided by integer divided by 2. So basically for I in range this to the minus 1 minus 1. So for each parent node, we just call heapify, self.heapify. Okay, so that's our basic framework. So now let's start implement this heapify function. Before that, we need to get n. So n equals the length of nums. So now let's go to the heapify implementation. So for heapify implementation, given the parent node index I, the left child is 2 times I plus 1, the left child node index. And then the right child node index is 2 times I plus 2. And then we need to do the comparison to compare the parent node value with the children value. So in that case, let's just use a variable. We call it max index. At the very beginning, we assign the parent index to the max index. It denotes the index of the maximum of the node with the maximum value. Let's do the comparison. So if max index if the value, let's say the numbers I, is less than the numbers left, it means, okay, the left child node is larger. So in that case, the max index equals the index of the left child node. So if the nums are actually here, let's do a max index. If left max index is less than nums right, so in that case, the max index equals right. So why am I writing this way? So let's say first we compare its parent node with the left child because initially max index equals the parent node index. And then if the parent node value is less than the left child, now the max index becomes the index of the left child. And then we continue comparison because if both left and the right child are larger than the parent node, we want to pick the larger one from the left and right child. So that's why we continue comparison. And then also, let's say in the line 82 and 83, if the left child node is not greater than the parent node, so in that case, we do not do this assignment. So the parent index is, the max index is still remain at I. So in that case, this line 84 and 85, we just continue the comparison with the right child. So after the comparison, let's say if the max index is not I, which means we need to swap the parent node with its child node value. Then we do the swap. That is numbers, the max index numbers I equals numbers I, and then numbers max index. So we do the swap. So after the swap, call Heapify to the call Heapify for the swapped child node. So in that case, we call self.heapify for this nums, and then for the swapped child node. So in that case, the node becomes the max index because that's the index representing the swapped child node. However, this Heapify solution will not work. Why? What if given I, we only have the left child, but we do not have the right child? In that case, this one will become out of index. What if given I, we do not have any child, it's just a root node? Both left and right will become out of index. So we need to check that. So we need to have something like the represent the length of the string, length of the array. So in that case, we need to add condition. If left less than n, and if right less than n, to make sure that the left child node index and the right child node index are within n. Then how did we get this n? So we can get this n from the as input to this function. So that's kind of the complete Heapify function. It has three inputs. One is the array, and then the second input is the n, indicates the length of this array, and I equals the node where we apply Heapify to. So given this parent node, we calculate the left child node index, right child node index, and then we just compare the value with the left of the parent node with the left child and right child, and then in order to find the child with the maximum value that is larger than the parent value, and then if we find the child value that is larger than the parent value, we do the swap, and then after the swap, we call Heapify for the swap child node. So that's kind of the logic for the entire Heapify function. So in that case, we also need to modify this line of code to add I, to add n. And then now we have a max heap that we created from this input array num. So now we need to sort. So basically to sort that one, so we loop through for I in range n minus 1, and then 0 minus 1. And then we swap nums 0, that is always the maximum value of the current heap. We want to put it to the end of this array to sort it in order. So that's why we are doing the swap. So after swap, reheapify. So we call self.heapify on numbers. And then in this case, we reduce the heap size by 1. So for the first iteration, I equals n minus 1. And then when we heapify, we do not consider the element at the position of n minus 1. So in that case, the size of a heap becomes n minus 1. It reduces 1 from the original length n. That's why this is I. And then when we reheapify, we always reheapify from the root value, that is from the index 0. Why? Because let's say if we reduce the heap size by 1, we do not consider that element we swapped. Then in that case, the remaining items, all the subtrays are already max heap except for the root value. So that's why we only need to reheapify the root node. So that's why in this input, each time we just reheapify the root node, because the remaining part of the tree are still the max heap. Sorry, the remaining subtrees are still max heap after we reduce the size of this heap by 1. So that is the code for the heap sort. So let's return the numbers, return our sorted array. So this is the entire code. So let me run this one. Okay, it passed the initial test cases. And it's an accepted solution.